In the video we just finished, we talked about a quantity called radiation power density, which is basically just the result of the pointing vector. And now I want to introduce another concept called radiation intensity. And radiation intensity is a directional quantity that tells us how strong the antenna radiates in a particular direction. And it is defined as the power radiated from an antenna per unit solid angle. And to calculate radiation intensity, we multiply radiation density or power density by the square of the distance. So we define a new quantity. It's called radiation intensity. It's measured in watts per steradian or watts per solid angle, and it is calculated by multiplying the square of the distance, r squared, by r, the result of the pointing vector, or the power density of the antenna. So how is this different than power density? Why do we do this? Well, radiation intensity is saying something about the source of the radiation. Since we multiplied by this r squared, there isn't a distance dependent anymore. Remember, this was a function of r theta phi. So since we multiply by r, we get rid of this r dependency. So radiation intensity is instead telling us how strongly the radiation is pointing in a certain direction, and it's only dependent on the angular directions, theta and phi, not r. So u will always be a function of theta and phi, not of r theta phi. So if I were to continue with the analogy of the sun, radiation intensity tells us if the sun is radiating more strongly in a particular direction. It doesn't say anything about how much power we'd absorb at a specific distance away from the sun. And by that I mean radiation intensity is independent of the distance from the antenna. And radiation patterns can be thought of as plots of radiation intensities. The radiation shapes, or the antenna shapes, can be thought of these plots of radiation intensity. And most often we're interested in a quantity called average radiation intensity, which is found by dividing the radiation intensity by the area of a unit sphere. And we call that U average. And it's just we take the total power irradiated and we divide it by 4 pi watts per steradian. And it's measured in watts per steradian. So average radiation intensity for a given antenna represents the radiation intensity at a point source producing the same amount of power as the antenna. So the last thing I want to point out when we're talking about radiation intensity is that just like power, a lot of times radiation patterns are plots of normalized radiation intensity. And by that I mean that the normalized radiation intensity of theta comma phi is just equal to the radiation intensity at any point in space divided by the maximum value of radiation intensity. So again, this is going to be unitless. I can convert it into watts per steradian divided by watts per steradian goes to no units. I could put it in dB by taking 10 log of that. And so a lot of times people call this the antenna pattern. And I just want to make a note, just a little mathematical note. So U of theta comma phi is equal to r squared. We just take r squared and we multiply it by the power density function, which is a function of r theta phi. And as we just showed, un of theta comma phi is just u theta phi divided by u max. And so that would equal to r squared, un of theta comma phi is equal to r squared times the power density function divided by u max. Well, u max is just going to be r squared times p max. And these r squareds are going to cancel out, which is just equal to Pn of theta comma phi. So the normalized radiation intensity is exactly the same as the normalized power density function. So some people say radiation plots or antenna plots are plots of radiation intensity. Other people normalized radiation intensity. Other people said that they're plots of normalized power density functions. Semantics, they're the same thing. So if we have an antenna plot, it is giving us normalized power. It is giving us radiation intensity. It doesn't discriminate between the two.